A single particle of light drifts toward two possible paths. Send enough of them, one at a time, and something impossible happens. They pile up into stripes of bright and dark, as if each lonely photon somehow passed through both openings at once and interfered with itself. But the instant you learn which path it took, the stripes vanish. For a century, physicists argued over why. Einstein thought it was clumsy equipment. Bohr thought it was a law of nature. Then, in 2025, a team at MIT did something Einstein and Bohr never imagined possible. They replaced the slits with single atoms, cooled to a whisper above absolute zero, and the mystery only deepened. What they found is stranger than either genius guessed, and no one was even looking. If this is the kind of science that pulls you deeper, take a second to like and subscribe. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Are you comfortable? Now, let's begin. Picture the smallest flash of light that can possibly exist. Not a beam, not a ray, not the glow of a lamp or the shine of a distant star. Just one indivisible packet of light, the very least the universe will ever hand you. Cut it in half, and you get nothing. It is the floor, the bottom rung, the single brick from which every sunrise and every laser and every glimmer you have ever seen is built. Physicists have a name for that brick. They call it a photon. Here is the first thing you need to sit with. A photon is not a tiny glowing ball, even though almost everyone imagines it that way. It is a quantum of the electromagnetic field, which is a careful way of saying it is the smallest chunk of light that can be created or absorbed as a single, complete unit. When it lands on a detector, it lands all at once, in one spot, delivering one discrete kick of energy. It does not smear itself across the screen like spilled paint. It arrives like a single raindrop hitting a window pane at one point, with a definite little tap. That behavior, arriving whole and localized at a single place, is what physicists mean when they say a photon acts particle-like. Particle-like means countable. It means here, not there. It means one. So far, so reasonable. And if the story ended there, light would be simple, and this video would not exist. But light has a second personality, and the two do not get along. Long before anyone knew photons existed, people already suspected that light was a wave. And to understand what a wave even is in this context, forget light for a moment and think about water. Drop a single pebble into a still pond, and a ring of ripples spreads outward. Drop two pebbles a short distance apart, and something more interesting happens. The two sets of ripples spread until they overlap. Where the crest of one ripple meets the crest of another, they stack up into a taller crest. Where the crest of one meets the trough of another, they flatten each other into nothing. Reinforcement in some places, cancellation in others. That crisscrossing pattern of stronger and weaker, of piled up and wiped out, has a name. It is called interference. And interference is the unmistakable signature of a wave. Particles do not do it. Waves always do. Now hold that idea, because it is about to be aimed straight at light. The person who did the aiming was an English polymath named Thomas Young. Around the year 1801, Young was wrestling with a question that had split science for over a century. The great Isaac Newton had insisted that light was made of tiny corpuscles, little bullets streaming from their source. Others suspected light was a wave rippling through some invisible medium. Young decided to settle it with an experiment so simple you could almost sketch it on a napkin. He let light fall on a barrier with two narrow, closely spaced openings cut into it, two slits. On the far side, he placed a screen to catch whatever came through. And here is the reasoning that makes the experiment brilliant. If light were truly a stream of little bullets, you would expect two bright bands on the screen, one lined up behind each slit, like paint sprayed through two gaps in a stencil. Two openings, two stripes of light, clean, obvious, done. That is not what appeared. Instead, Young saw a whole series of bright and dark bands marching across the screen, many more than two, evenly spaced, fading out toward the edges. Bright, dark, bright, dark, bright. It was exactly the pattern you would get if two sets of waves had spread out from the two slits and crisscrossed on their way to the screen, reinforcing each other in some places to make the bright bands, and cancelling each other in others to leave the dark ones. It was interference, written in light. Young had caught light behaving like a wave, and for most of the next 100 years, the matter seemed closed. Light was a wave, case shut. Except the universe was not finished with the joke. Fast forward through the 1800s and into the early 1900s, and physics went through an earthquake. Scientists discovered that light, this supposedly smooth and continuous wave, actually delivers its energy in discrete lumps. It comes in packets, it comes in photons. Light was a wave. The double-slit stripes proved it. And light was also a particle. The discrete energy packets proved that too. Both were true. Both were solidly, experimentally, undeniably true, and they seem to flatly contradict each other. For a while, you could almost wriggle out of the contradiction with a comfortable excuse. Maybe, you might say, a beam of light contains countless photons all at once, and the wave pattern is just a crowd effect. Maybe the individual photons are ordinary little particles, and the stripes only appear because millions of them are jostling together, bumping and colliding, and the interference is some kind of traffic pattern that emerges from the swarm. Under that story, each photon is still just a bullet. The wave is only an illusion created by having a huge number of bullets in flight at the same time. It is a tidy story. It is also completely wrong. And the way we know it is wrong is the most unsettling part of this entire experiment. Because you can turn the light down. Imagine dimming the source so far that photons trickle out one at a time. Not a flood, not a stream, a drip. So faint that a single photon leaves the source, crosses the apparatus, and strikes the screen entirely alone, and only after it has landed does the next one begin its journey. At any given instant, there is just one photon anywhere in the machine. There is no crowd. There is no swarm. There is no traffic. Whatever a photon does, it now has to do it completely by itself, with no companions to bump into. So what happens? At first, nothing that looks like a wave at all. The first photon strikes the screen and leaves a single dot. One tiny point of light, arriving whole, at one location, exactly as a particle should. The second photon lands somewhere else, another lonely dot. The third, another. If you watched only the first handful, you would swear you were watching particles, one at a time, splattering more or less at random across the screen, like the first few drops of rain on dry pavement. There is not a stripe in sight. There is no pattern, just scattered, isolated points. But keep going. Let the dots accumulate. 10 of them. 100. 1,000. 10,000. And as the count climbs, something begins to surface out of the randomness, the way a photograph slowly emerges in a developing tray. The dots are not landing evenly. Certain regions of the screen are collecting more and more of them, while other regions are staying strangely empty. Bands begin to appear. Bright bands where the dots pile up thick. Dark bands where almost none land. Keep waiting. Keep counting. And the picture sharpens into the unmistakable striped pattern of interference. The exact same fringes Young saw 2 centuries ago. Bright, dark, built one solitary dot at a time. Stop and feel how strange that is. Each photon crossed the machine alone. Each one arrived as a single localized dot, behaving like a particle. Yet collectively, over thousands of independent, isolated arrivals, they assembled a wave pattern that requires 2 overlapping paths to exist. A pattern of interference. And interference, remember, is what happens when a wave passes through both slits at once and crisscrosses with itself. But there was only ever one photon in the machine at a time. There was nothing for it to interfere with. Nothing except, somehow, itself. This is not a thought experiment or a theorist's daydream. It has been done repeatedly for over a century. As early as 1909, a young physicist named Geoffrey Taylor dimmed a light source so severely that only the faintest trace of light crossed his apparatus at any moment, then left it exposed for months to slowly gather the arrivals. The interference fringes appeared anyway, at intensities so low that the crowd explanation was already in trouble. Decades later, with better technology, physicists watched the pattern build up dot by dot in real time and filmed it. They even ran the same experiment not with photons but with electrons, and later with whole molecules containing dozens of atoms. Hefty things you would never call waves in a million years. Every time, the same result. Fire them one at a time, wait, and the wave pattern condenses out of a mist of individual particle-like dots. There was still one nagging worry a careful skeptic could raise about all of this, and physics eventually had to close it. Dimming a lamp very low does not guarantee the photons come strictly one at a time. Ordinary light dribbles out in an uneven, clumpy way, and now and then 2 photons might sneak through together, which would leave the door open to the crowd explanation after all. So in the 1980s, a group of French physicists, among them Alain Aspect, built a source that released photons genuinely one at a time, and then sent each one at a half-silvered mirror, a splitter that a photon can either pass through or bounce off. If a photon were secretly divisible, some of it would go each way, and both detectors would sometimes fire together. They never did. Every photon went one way or the other, whole and undivided, exactly as a single particle must. And yet, when those same certified single photons were sent through a 2-path arrangement instead, they built up interference all the same. This was the clincher. Indivisible when you test it for wholeness, wave-like when you let its paths stay open. The same photon, both at once. The crowd explanation was dead for good. So what is actually going on? How can a single indivisible photon, which strikes the screen at one point like a proper particle, nevertheless behave on its way there as though it were a spread out wave, sampling both slits at once? This is where we have to introduce the idea that sits at the dark heart of quantum mechanics. And we have to introduce it very carefully, because this is exactly the place where popular explanations go off the rails. The concept is called superposition, and the tempting, sloppy way to describe it is to say that the photon literally splits in half. That one copy goes through the left slit and another copy goes through the right, and the 2 copies meet up again on the far side and interfere. Please gently throw that picture away. It is not what happens. The photon does not split. You never ever detect half a photon coming out of one slit and half out of the other. Put a detector at each slit, and you will always catch the whole photon at exactly one of them, never a fraction at each. Superposition is subtler and stranger than splitting. Here is a more honest way to hold it. When a photon travels from the source to the screen, and when nothing about the setup records which slit it went through, then the two possible paths, through the left and through the right, are not two separate things that happen to two separate copies. They are two indistinguishable alternatives for the one photon, and in quantum mechanics, indistinguishable alternatives do not simply sit side by side as separate possibilities. They combine. They add together as waves add together into a single blended description of the photon's journey. Physicists track each path with a quantity called a probability amplitude, and these amplitudes carry something like the crests and troughs of a wave. When you add the amplitude for the left path to the amplitude for the right path, they reinforce in some directions and cancel in others, precisely the way Young's two sets of ripples reinforced and cancelled. The result is a pattern of places where the photon is very likely to land and places where it is essentially forbidden to land. That pattern of likelihoods is the interference pattern. It helps to make that adding together concrete, because amplitudes reinforce and cancel can sound like hand waving until you can picture it. So picture this. Assign to each path a little arrow, like the hand of a tiny clock. The arrow has a length, and it has a direction it points. The length encodes how likely that path is on its own, and the direction, the angle the arrow is turned to, encodes a kind of quantum phase, a bookkeeping of where the photon sits in its cycle, which advances steadily as the photon travels farther. Think of the arrow as slowly rotating, one full turn after another, as the photon covers distance, the way a clock hand sweeps around its face. Now, to find the odds of the photon landing at a particular point on the screen, you take the arrow for the left path and the arrow for the right path, and you add them, not like ordinary numbers, but tip to tail, the way you would add two steps taken in different directions. And here is where everything comes from. If the two paths to that point are the same length, both arrows point the same way, and adding them tip to tail gives one long arrow. The probability that the photon lands there is set by the length of that final combined arrow, squared. So a long arrow means a very likely spot, a bright band. But if the two paths differ in length by just the right amount, one arrow ends up pointing opposite to the other, and adding them tip to tail folds them back on each other, until they shrink to almost nothing. A vanished arrow means a forbidden point, a dark band. Sweep your eye across the screen, and the two path lengths change smoothly from point to point. So the two arrows fall into step and out of step over and over, long, short, bright, dark. That marching alternation of reinforcement and cancellation, born from nothing more than two little arrows turning and being added together, is the interference pattern. And it is why a single photon's odds are carved into stripes. This picture also cracks open a small paradox that ordinary intuition cannot swallow. With both slits open, some points on the screen are dark, places where almost no photons ever land. Now cover one slit. You have taken light away, you have given the photon fewer ways to reach the screen, and yet those formerly dark points suddenly fill with light. Removing a path made a dark spot bright. Open the second slit again and the darkness returns. More openings, more ways through, and yet less light in certain places. No stream of little bullets could ever behave this way, because bullets from two openings can only ever add up, never subtract. Only something that can cancel, something with those turning arrows that can point against each other, can take two sources of light and produce, in the right spot, perfect black. That single fact, that opening a second door can make a lit room darker, is the whole strangeness of the wave in miniature. So the fringes are not telling you that the photon went both ways as two little objects. They are telling you that, as long as the path is genuinely unknowable, the photon's journey has to be described by both possibilities woven together into one, and that woven together description has ripples in it. Each individual photon then lands as a single dot, but the odds governing where that dot can appear are shaped by the ripples. Send enough photons, and the odds paint themselves onto the screen as bright and dark bands. The wave is not made of photons crowding together. The wave lives in the possibilities for each single photon, one at a time. Read that again, because it is the crux. The wave is in the possibilities, not in the crowd, not in the substance of the light. In the range of things a single indivisible photon could do when the universe has not pinned down which slit it used. And that phrase, when the universe has not pinned down which slit it used, is the loose thread that unravels everything. Because the entire pattern hangs on one delicate condition. The two paths must be indistinguishable. There must be no way, anywhere, to tell which slit the photon actually passed through. The moment the condition holds, the amplitudes add, the ripples appear, and the fringes emerge. The photon behaves wave-like. It is spread across possibilities, which raises the obvious, irresistible, almost childlike question. What if we just look? The photon has to go through one slit or the other, doesn't it? It is a real thing. It has to take a real route. So what stops us from simply watching, from placing some clever little detector at the slits, from catching the photon in the act and writing down, for each one, left or right? We would learn which path each photon took. We would build up our striped interference pattern at the same time. And we would finally have both stories at once. We would see the particle taking its single definite route, and we would see the wave assembling its fringes, two personalities of light, caught together in one photograph. Mystery solved. It is the most natural experiment in the world to want to run. It feels like it must work. Of course you can watch which slit it goes through. Of course the stripes will stay. Why on earth would checking the photon's route have anything to do with a pattern building up on a screen far away? The path and the pattern seem like completely separate facts about the world. Measuring one should leave the other untouched. That is how everything in ordinary life behaves. You can note which turnstile a person walks through without changing where they end up on the platform. You can clock which lane a car takes without altering where it parks. Information is supposed to be free. Looking is supposed to be safe. Hold on to that certainty. Hold on to how obvious it feels that you could have both, because it is precisely this obvious, reasonable, common sense expectation that the universe is about to take out behind the building. The instant you find a way, any way at all, to learn which slit the photon used, the stripes do not merely dim. They vanish. The fringes collapse. The wave pattern that took thousands of patient photons to assemble simply refuses to appear, and in its place you get exactly the two dull bands you would expect from ordinary bullets, one behind each slit. Knowledge of the path and the existence of the wave turn out to be locked in a trade. and you cannot cheat the exchange rate. And the deepest question, the one that would consume the two greatest physicists of the 20th century, and would not be laid bare in its purest form until a laboratory at MIT got its hands on individual atoms nearly 100 years later, is this: why? Why should merely knowing the root erase the wave? What is the physical connection between a fact in your notebook and a pattern of light on a distant screen? Is it a limitation of clumsy equipment? A smudge introduced by detectors too crude to peek without shoving? Or is it something woven into the fabric of reality itself? A rule the universe enforces, no matter how gentle, how delicate, how nearly invisible your looking becomes. That question is where the real story begins. And to reach the strange, beautiful answer, we first have to walk into the most famous argument in the history of physics. Between a man who was certain he could beat the trade and a man who was certain that he could not. Because before anyone built slits out of atoms, two titans stood at a chalkboard and fought over a spring. Let us name the thing that vanished. When you found a way to learn which slit the photon used, the stripes disappeared. So the quantity that matters, the thing you gained that cost you the wave, is knowledge of the root. Physicists have a precise term for it. They call it which path information, or sometimes which way information, and once you understand what it really means, the whole mystery sharpens into a blade. Which path information is exactly what it sounds like. It is any physically recorded answer to the question, through which slit did this photon go? Notice the careful wording. Not any answer a person happens to have read. Not any answer someone is consciously thinking about. Any answer that exists, anywhere, in any physical form, written into any object in the world. If somewhere in the universe there sits a reliable record that says this particular photon went left, and that one went right, then which path information exists? And the astonishing, load-bearing fact of this entire story is that the mere existence of that record, whether or not any living creature ever looks at it, is enough to destroy the interference pattern. We will return to that point with force later, because it is where nearly everyone's intuition breaks. For now, plant a flag on it. Interference does not care about eyes. It cares about records. It cares about whether the information is out there to be had. Keep the paths truly indistinguishable, leave no trace anywhere of which route was taken, and the wave lives. Allow the world to imprint the route into any object at all, and the wave dies. This trade, this strict and unforgiving exchange between knowing the path and seeing the wave, has a name too, and it belongs to a Danish physicist who spent his life turning quantum strangeness into principles. His name was Niels Bohr, and he called it complementarity. Complementarity is one of the deepest ideas in physics, and it is often badly explained. So slow down for it. It does not say that light is sometimes a wave and sometimes a particle, as if it were flipping a coin or changing costumes. It says something stricter and stranger. It says that the wave nature and the particle nature are two complementary descriptions of the same thing, both real, both valid, but which can never be fully displayed in the same experimental arrangement at the same time. You can build a setup that reveals the wave, and it will hide the particle. You can build a setup that reveals the particle, the definite path, and it will hide the wave. What you cannot do, ever, is build one setup that reveals both completely. The two faces are not in conflict. They are in rotation. When one turns toward you, the other turns away. That, in a sentence, is what complementarity claims. And complementarity is not a lonely idea. It rests on the shoulders of an even more famous one, a principle so notorious that its name has leaked out of physics and into everyday speech, usually mangled. The uncertainty principle, formulated by the young German physicist Werner Heisenberg in 1927, it states that certain pairs of properties of a quantum object are linked in a peculiar way, so that the more precisely you fix one, the more inescapably blurred the other becomes. The most famous such pair is position and momentum. Position is simply where something is. Momentum, for our purposes, is a measure of its motion, its mass multiplied by its velocity, the quantity that tells you how much of a push it carries and in what direction. Here is the part people get wrong. The uncertainty principle is not a statement about clumsy instruments. It is not saying that our rulers are too coarse or our detectors too rough to measure both at once. It is saying something far more radical, that a quantum object does not itself possess a perfectly sharp position and a perfectly sharp momentum simultaneously. The sharpness of one is bought with the fuzziness of the other, and the trade is written into nature, not into our tools. Pin down where a particle is with great precision, and its momentum spreads into a smear of possibilities. Pin down its momentum with great precision, and its location dissolves into a cloud. You are not failing to measure a hidden truth. There is no hidden sharp value waiting to be caught. The fuzziness is the truth. There is a famous way of first meeting this principle that Heisenberg himself reached for, and it is worth a moment because it plants a seed this whole story will later dig up. Imagine you want to see exactly where a tiny particle is, so you do the obvious thing. You shine light on it and look, the way you locate anything. But to pin down a very small position, you need light of a very short wavelength, and short wavelength light carries a hard punch of momentum. So the very photon you bounce off the particle to find it delivers a kick that shoves the particle's motion in an unpredictable way. Look sharply enough to nail the position, and you have disturbed the momentum. This little parable is called Heisenberg's microscope, and for decades it shaped how people pictured the uncertainty principle, as though the fuzziness was simply the clumsy result of measurement, always jostling what it touches. Bohr, tellingly, was never fully satisfied with that telling. He argued the disturbance picture, though not wrong, was too shallow, that the uncertainty was not merely an accident of rough handling, but something rooted in the wave nature of matter itself, prison even before any clumsy kick. This disagreement, disturbance on one side and something deeper on the other, is not a footnote. It is the exact fault line the MIT experiment, nearly a century later, would finally stand astride and resolve. Hold on to it. Was it the shove, or was it something more fundamental? Einstein and Bohr were about to have that very fight, in the most concrete terms imaginable. Now you have the three pieces you need. Which path information, the recorded answer to which slit. Complementarity, the rule that path and wave cannot both be fully shown. And the uncertainty principle, the deeper law that makes complementarity bite. With these three in hand, we can finally walk into the room where the greatest argument in the history of physics took place. The year is 1927. The place is Brussels, at a gathering called the Solvay Conference, a rare summit where the finest physicists on Earth crowded into a single hall to fight over what their new quantum theory actually meant. And it needed fighting over, because quantum mechanics had arrived like a stranger who rearranges your furniture. It worked. Its predictions were flawless, but it insisted on a world governed by probabilities rather than certainties. A world where you could not, even in principle, know everything at once. To many, that felt less like a discovery and more like a surrender. No one felt that more sharply than the most famous scientist alive, Albert Einstein. It is worth pausing to correct a myth right here, because it will matter for how we read this whole confrontation. Einstein was not a fool about quantum mechanics, and he was not its enemy. He helped invent it. It was Einstein who first proposed, decades earlier, that light comes in discrete packets of energy, the very photons this whole story rests on, and he won his Nobel Prize for exactly that insight, not for relativity. When Einstein pushed against quantum mechanics, he was not pushing from ignorance. He was pushing from conviction. He believed, deep in his bones, that nature had a definite reality underneath, that things possessed real properties whether or not anyone measured them, and that the probabilities of quantum theory were a sign the theory was incomplete, a temporary fog concealing a clockwork we had not yet uncovered. His famous line that God does not play dice was not a joke, it was a creed. So Einstein set out to break the new theory, not by dismissing it, but by outthinking it. He would design an experiment on paper, a thought experiment that used the theory's own rules to trap it in a contradiction. And the double-slit experiment, with its maddening trade between path and pattern, was the perfect battlefield. If Einstein could find a way to know which slit the photon went through and still see the interference fringes, then complementarity would be broken. The wave and the particle would both stand revealed at once, and quantum mechanics would be exposed as the incomplete, half-finished description he suspected it to be. He thought he had found the way. And his weapon was a spring. Follow his reasoning, because it is genuinely clever, and it is built on a rock-solid piece of physics that even Bohr could not deny. When a photon passes through a slit and bends toward one part of the screen rather than another, its direction of motion changes, and whenever the direction of a moving thing changes, its momentum changes, because momentum includes direction. But there is an iron law in physics called the conservation of momentum, which says momentum can never simply appear or vanish. It can only be passed from one object to another. So if the photon's momentum changed as it went through the slit, something had to absorb the difference. Something had to receive an equal and opposite kick. And the only thing there to receive it was the barrier itself, the wall the slit is cut into. Think of what happens when a person standing on a frozen pond throws a heavy ball. The ball flies forward and the thrower slides backward across the ice. The thrower did not intend to move, but throwing the ball forward demanded, by the conservation of momentum, that the thrower recoil backward. That backward slide, that reaction kick, is called recoil, and it is one of the most reliable phenomena in all of physics. A rifle recoils into the shoulder. A rowboat drifts backward as you step off it onto the dock. Every action buys an equal and opposite reaction. Einstein's insight was that the same thing must happen at the slit. As the photon veers, it delivers a tiny recoil kick to the barrier. If the photon bends towards the top of the screen, it nudges the barrier ever so slightly toward the bottom, and if it bends toward the bottom, it nudges the barrier toward the top. The kick is unimaginably small, because a photon carries a whisper of momentum, but it is not zero. And Einstein reasoned, brilliantly, that the size and direction of that recoil depends on which slit the photon passed through, because the two slits sit at different places, and a photon reaching a given point on the screen has to bend by a different amount depending on which slit it started from. So here was the plan. Do not fix the barrier rigidly to the table. Instead, mount it on a delicate spring so that it can twitch freely in response to the faintest push. Make it light, make it sensitive, make it a trembling little thing poised to register the gentlest nudge. Now, fire your photons through the two slits, one at a time, and watch two things at once. Watch the screen where the interference fringes build up dot by dot, and watch the recoil of the sprung barrier reading off, for each photon, the tiny kick it delivered, and inferring from that kick which slit it must have used. If it worked, Einstein would have his triumph. He would hold, in his two hands, the complete story of every single photon. He would know its path, read cleanly from the barrier's recoil, and he would see the wave, written in fringes on the screen. Particle and wave, path and pattern, both fully revealed in one experiment. Complementarity shattered, the trade beaten. Quantum mechanics caught in the act of hiding something that was really there all along. It was, on its face, a beautiful attack. It used only conservation of momentum, which nobody disputed. It required no exotic trickery. It felt airtight. And it landed the argument squarely in Bohr's lap. The story goes that Bohr was shaken, that he spent a restless, sleepless stretch pacing and muttering, working through the machinery of Einstein's trap, hunting for the flaw he was certain must be hiding inside it. Because Bohr's entire understanding of quantum mechanics said the trap could not work. Complementarity had to hold. If Einstein was right, Bohr's worldview collapsed. So Bohr did the only thing a great physicist can do when cornered. He took Einstein's own weapon apart, piece by piece, and turned it around. And the flaw, when Bohr found it, was exquisite. It was hiding in the spring. Here is the counterstroke, and it is worth walking through slowly, because it is the intellectual seed of everything the MIT experiment would eventually make real. Einstein's whole scheme depended on reading the barrier's recoil. To know which slit the photon used, you must measure the tiny kick the barrier received, which means you must measure the barrier's momentum, and measure it precisely enough to distinguish the kick from one slit from the kick from the other. The kicks are minuscule and nearly identical. To tell them apart, you need to know the barrier's momentum with exquisite sharpness. But now recall the uncertainty principle. Position and momentum are a linked pair. The more precisely you fix the barrier's momentum, the more inescapably uncertain its position becomes. This is not about your measuring devices being crude. It is the barrier itself, as a quantum object, refusing to possess both a sharp momentum and a sharp position at the same time. And here is the killing detail. To read the recoil precisely enough to reveal the photon's path, you must pin the barrier's momentum so tightly that, by the very same law, the barrier's position smears out into a blur. And the position of the barrier is not a harmless detail. It is everything. Because where the slits sit determines where the bright and dark fringes fall on the screen. The entire interference pattern is anchored to the exact location of the two openings. Picture a picket fence casting a pattern of shadows. Jiggle the fence back and forth, even slightly, and the shadows slide and smear. Now let the barrier's position become genuinely uncertain, blurred over a range, and the fringe pattern smears along with it. Each photon lands according to a slightly shifted version of the pattern, and when you add up thousands of them, The bright and dark bands wash into each other and dissolve into a featureless smear. Exactly the same dull result you would get from ordinary particles. Do you see the trap snap shut? The instant you make the barrier able to reveal the path, by fixing its momentum sharply enough to read the recoil, you force its position to blur by exactly the amount needed to erase the fringes. The measurement that hands you the path is the very same measurement that destroys the wave. You cannot separate them. You cannot have one without paying with the other. The uncertainty principle stands guard over the trade like a bouncer who will let you carry out the path or the pattern, but frisks you at the door and confiscates whichever one you were not supposed to keep. This was Bohr's answer, and it was devastating precisely because it used Einstein's own physics against him. Einstein invoked conservation of momentum. Bohr accepted it completely, and then simply pointed out that if you take the recoil seriously as a real, measurable momentum, you must also take seriously the uncertainty that comes attached to any precise momentum measurement. Einstein had remembered one law of quantum physics and forgotten its partner. When both laws were applied together, the loophole sealed itself. Complementarity survived. The trade held. And it held not by luck, not by clumsiness, but because the same uncertainty principle that forbids sharp position and sharp momentum together is the very thing that ties path knowledge to fringe destruction with an unbreakable knot. Let us be careful and fair, because there is a subtlety here that will matter enormously by the end of this story, and glossing over it would cheat you. Bohr's original rebuttal leaned heavily on the physical recoil of a movable slit, on springs and momentum kicks, and the mechanics of a trembling barrier. And that framing, powerful as it was, left a lingering question hanging in the air, one that would take the better part of a century to answer cleanly. Was the destruction of the fringes really about information, about the world recording which path was taken? Or was it just about the mechanical jostling, the physical disturbance of a real barrier getting shoved around? Were the springs the reason, or were the springs a distraction? Because you can tell the story two ways, and for decades it was genuinely hard to separate them. Story 1 says the fringes vanish because knowing the path, having the information anywhere in the world, is fundamentally incompatible with the wave. Story 2 says the fringes vanish because measuring the recoil physically kicks and blurs the apparatus, and it is the kicking, the mechanical mess, that smears the pattern. Both stories predict the same outcome in Einstein's setup. Both point at the spring. And for as long as your slits were macroscopic objects mounted on real springs, you could not cleanly tell which story was true, because the information and the mechanical disturbance were welded together. Every time the barrier recorded the path, it also got physically shoved. You could never pull them apart to see which one was really doing the killing. This ambiguity is not a small footnote. It is the crack that ran through the foundation of the double-slit story for nearly 100 years. Einstein and Bohr argued about springs and recoiling barriers because that was the language they had. They were interested in the limiting cases, the extremes where the wave was perfectly hidden or perfectly shown, but the messy, fascinating middle ground where you gain only a little path information and lose only a little of the wave, and where you might finally separate information from mere mechanical disturbance, lay largely unexplored. The debate ended not with a knockout, but with a truce. Einstein conceded the specific point. He could not beat Bohr's rebuttal, but he never truly accepted the worldview behind it, and he kept designing new thought experiments for years afterward, each one a fresh attempt to catch quantum mechanics hiding a definite reality. Each one Bohr answered. The two of them circled this question in one form or another for the rest of their lives. The grandest of those fresh attempts came 3 years later, at the next Great Solvay gathering in 1930. And it was so audacious that it briefly looked as though Einstein had finally won. This time, he did not aim at position and momentum. He aimed at a different pair the uncertainty principle binds together, energy and time, and he built, on paper, a device to defeat it. Picture a box, its walls lined with a perfect mirror, filled with light. In one wall sits a shutter, and the shutter is worked by a clock inside the box. The clock is set to flick the shutter open for one brief, precise instant, just long enough to let a single photon escape, and then snap it shut. Because the clock controls the shutter, you know the exact moment the photon left. That is the time. Pin down as sharply as you please. Now for the energy. Einstein reached for the most famous equation he ever wrote. The one that says energy and mass are the same thing wearing different clothes. A photon carries energy, and letting it escape makes the box lighter by a whisper, since the energy that leaves takes its mass equivalent with it. So weigh the box before the photon escapes, weigh it again after, and the tiny difference tells you, through that equation, the exact energy of the escaped photon. Time from the clock, energy from the scale, both as precise as you like, and the energy-time uncertainty relation lies in ruins. Einstein, by the accounts of those present, was quietly delighted. Bohr, by the same accounts, was stricken and spent the evening going from person to person, pale and agitated, insisting it could not be right, but unable to say why. He found the answer, the story goes, by morning, and its beauty is almost cruel, because he defeated Einstein using Einstein's own greatest creation. To weigh the box, Bohr pointed out, you must hang it from a spring and read a pointer against a scale, letting it settle to its new weight. Reading that pointer means fixing the box's position, and fixing a position by the uncertainty principle injects an unavoidable spread into the box's vertical momentum. But here is the master stroke. That box sits in the Earth's gravitational field, and Einstein's own general theory of relativity had established, years earlier, that a clock ticks at a rate depending on its height in a gravitational field. Clocks lower down run slightly slower. Clocks higher up, slightly faster. So the moment you let the box shift by an uncertain amount up or down in order to weigh it, you make the height of the clock uncertain, which makes the clock's ticking rate uncertain, which smears out the very time you were trying to measure so precisely. Work the numbers, and the blur in the energy and the blur in the time multiply out to exactly the amount the uncertainty principle demands, not a hair less. Einstein had tried to break the energy-time relation, and Bohr had saved it by turning gravitational time dilation, a jewel from relativity, into the weapon of defense. It is remembered as one of the greatest intellectual counterpunches in the history of science. Einstein never mounted a frontal assault on the uncertainty principle again. None of this was cold or hostile, and that matters for understanding what was really at stake. Einstein and Bohr were not enemies. They were something rarer. Two people who disagreed at the deepest possible level and respected each other enormously for it. They needled each other with real affection. When Einstein pressed that same objection about God and dice, Bohr is said to have shot back that Einstein should stop telling God what to do. They argued in hallways, over meals, across decades and continents, and each sharpened the other. Einstein never converted. To his final years, he believed quantum mechanics, for all its flawless predictions, was an unfinished portrait of a deeper, more definite reality waiting to be uncovered. Bohr believed the theory was already complete, and that the definiteness Einstein longed for was a comfort the universe simply does not offer. Neither lived to see the argument settled in a laboratory. That would take another lifetime, and a technology neither could have dreamed to finally build the slit they had only ever drawn in chalk. For all that the two of them never settled the meaning, something quieter and more useful was happening to the mathematics in the decades that followed. Bohr had framed complementarity as an either slash or wave or particle, this door or that one. But later physicists sharpened it into something far more precise, a sliding scale rather than a switch. They defined two numbers. One they called the distinguishability, a measure of how much which path information is available in the world, running from 0, no clue at all, up to 1, a perfect record of the route. The other they called the visibility, a measure of how crisp the interference fringes are, running from 1, bright and sharp, down to 0, washed flat. And they proved a strict relationship binding the two, a kind of budget the universe refuses to overspend. You may divide a fixed allowance between distinguishability and visibility however you like, but the two can never together exceed it. Push distinguishability up, and visibility must fall by a precisely fixed amount. Pull it back down, and the fringes must sharpen again by exactly as much. This was the modern form of Bohr's idea, and notice what it promises that the old either-or did not. It promises a whole continuous middle, an entire curve of in-between states where you hold a little path information and keep a little of the wave, in a proportion the equations pin down exactly. Bohr and Einstein had fought over the endpoints, the extreme corners where the wave is perfectly shown or perfectly hidden. But the real content of complementarity, its testable heart, lives in that sloping middle ground, and it went almost entirely unprobed for decades. To walk along that curve, to sit at a chosen point and dial the trade smoothly by hand and check whether the universe truly honors its budget, you would need a control over single quantum objects that simply did not exist in the 20th century. You would need to build a slit whose fuzziness you could turn like a dial. You would need, in other words, exactly the machine nobody could yet build. And underneath all of it sat the thing neither of them could fully resolve with the tools of their time. The whole magnificent argument rested on apparatus, on springs, on movable barriers, on detectors that had to touch the photon or the slit and, in touching, disturb it. As long as that was true, a stubborn skeptic could always mutter the same complaint. Maybe the fringes only die because your equipment is clumsy. Maybe if you had a gentle enough detector, a delicate enough spring, a soft enough touch, you could sneak a look at the path without spoiling the wave. Maybe complementarity is not a law of nature at all, but merely a practical limit of machines that are too crude to peak without shoving. Maybe, for a century, that maybe could not be fully killed, because no one had ever built the experiment clean enough to leave nothing to blame. Every real double-slit setup came with baggage, slits cut into solid material, detectors made of atoms and wires, barriers with mass and springs and vibrations. Somewhere in all that machinery, a skeptic could always imagine a loophole hiding, a place where the fringe destruction was really just mechanical clumsiness, dressed up as a deep principle. So the question that Einstein and Bohr left on the table, the question that hung in the air for 100 years, was this: what would happen if you could strip the experiment down to nothing? If you could throw away the solid barrier, throw away the springs, throw away every clumsy detector, and build the slit itself out of the smallest, purest, most irreducibly quantum object that exists? What if the slit were a single atom, so simple and so exposed that there was nothing left to blame? No springs to hide behind, no mechanical mess to accuse? Would the trade between path and wave still hold? Would complementarity survive when there was no longer any apparatus to fault? Would the universe still enforce the boundary, even after you had taken away everything Einstein could have pointed at? For most of a century, that question could only be asked, never answered. The technology did not exist. You cannot mount a single atom on a spring. You cannot cut a slit into a wall the size of one atom and expect anything sensible. It was, quite literally, a Gedanken experiment, a thought experiment, the kind you argue about at a chalkboard in Brussels because you can never actually run it in a laboratory. And then, 100 years after two giants stood at that chalkboard and fought over a spring, a team of physicists in Cambridge, Massachusetts, cooled a cloud of atoms to within a hair of absolute zero, arranged them one by one with beams of laser light, and finally, for the first time in history, built the double-slit experiment out of individual atoms. No barrier, no springs, nothing to blame, but the atoms themselves. What they found is where this story turns from history into something far stranger. To be a thought experiment, you first have to trap the coldest matter in the universe. That is where the MIT team began. Not with photons, not with slits, but with a cloud of atoms and a mission to make them stand still. Everything about the double-slit mystery had, for a century, been tangled up with apparatus. Solid barriers, trembling springs, detectors made of countless atoms and wires. Every version of the experiment carried baggage a skeptic could point at and say, the fringes only died because the hardware was crude. So the physicists in Wolfgang Ketterle's group at the Massachusetts Institute of Technology set themselves a goal that Einstein and Bohr would have called impossible. They would throw away the barrier. They would throw away the springs. They would build the slits themselves out of the smallest, simplest, most irreducibly quantum objects that exist. Single atoms. And then they would see whether the trade between knowing the path and seeing the wave still held when there was nothing left to blame. The work was led by Vitaly Fedoseev, alongside Hanjin Lin, Yu Kun Lu, Yu Kyung Lee, and Jiahao Liu, under the eye of Ketterle, who had already won a Nobel Prize for coaxing atoms into some of the strangest states of matter ever made. Their result was published in the journal Physical Review Letters in July of 2025, and the timing was almost too poetic to be real. It landed on the 100th anniversary of the birth of quantum mechanics. In a year, the United Nations had formally named the International Year of Quantum Science and Technology. The Einstein and Bohr debate had taken place in 1927. Almost exactly a century later, in the same field, in the same argument, someone finally built the machine the two of them could only dream at. Start with the atoms, because getting them to hold still is a triumph on its own. Atoms at room temperature are frantic. They careen around at hundreds of meters per second, jittering and colliding, a blur of thermal chaos. You cannot build a precision slit out of something moving that fast, any more than you could cut a clean opening in a swarm of bees. So the first thing the team did was make the atoms cold, not refrigerator cold, not winter cold, cold beyond anything nature produces anywhere, a few millionths of a degree above absolute zero, the lowest temperature that can possibly exist, the point where all motion nearly ceases. They did it with light. This is one of those facts that sounds backward the first time you hear it, because we associate light with heat and warmth. But laser light, tuned with exquisite care, can be used to slow atoms down. Picture an atom rushing toward a laser beam. If the light is tuned just right, the atom preferentially absorbs photons coming at it head-on, and each absorbed photon delivers a tiny push against its motion, like a stream of ping-pong balls thrown at an oncoming truck. One ping-pong ball does nothing, but millions of them, precisely aimed, can bring even a fast atom to a crawl. Surround the atoms with beams from every direction, and whichever way an atom tries to move, it runs into a headwind of photons that saps its motion. Physicists call the result optical molasses, because the atoms behave as though they are wading through thick syrup. This technique of laser cooling is now a cornerstone of atomic physics, and it is how you get matter cold enough to sit still. Once the atoms were cold and calm, the team needed to arrange them. And here they reached for another trick made of light, called an optical lattice. When you overlap laser beams traveling in opposite directions, they interfere, exactly the way Young's two slits interfere, producing a standing pattern of bright and dark regions frozen in space. The bright and dark spots form a regular grid, a three-dimensional egg carton woven out of pure light. And atoms, it turns out, can be gently held in the wells of that egg carton. Each atom settles into its own pocket in the lattice, spaced a precise, regular distance from its neighbors, locked into a crystalline arrangement not by any solid material, but by the shape of the light itself. Now here is where it gets beautiful. Under the right conditions, the atoms arrange themselves so that exactly one atom sits in each well of the lattice. Not two, not zero, but precisely one, over and over, a perfect regular array of single atoms. This state has a name, a Mott insulator, and achieving it means you have built something extraordinary. You now possess a clean, orderly grid of individual atoms, each isolated in its own pocket of light, each one alone, over 10,000 of them, arranged like a perfectly spaced field of invisible marbles, held in place by laser beams. It is worth appreciating just how extreme the numbers behind this are, because they are what make the word idealized honest, rather than boastful. The atoms were rubidium, a soft metal in ordinary life, here reduced to a frozen quantum crystal. They were held at that same near-zero chill, so still that each atom's residual jitter shrank to almost nothing, quiet enough to keep a sharply defined place in the lattice for as long as the experiment needed. They were spaced by the geometry of the trapping light itself, sitting a fraction of a millionth of a meter apart, close enough that light scattering off two neighbors could still overlap and interfere. And there were more than 10,000 of them held in that rigid, regular order at once, everyone alone in its own sight. No barrier machined by human hands could ever approach this. A slit cut into metal foil has ragged edges, a finite thickness, a surface crawling with countless atoms, all of it introducing smudges and imperfections. Here there were no edges and no material at all, only individual atoms suspended in patterns of light, each one as clean and simple and identical as the laws of physics permit. That is what the physicists meant when they called it the most idealized double-slit experiment ever performed. They had not merely improved the old setup, they had removed almost everything that had ever made it a setup. leaving little more than single atoms, single photons, and the bare relationship between them. And each of those single atoms can now play the role of a slit. Sit with how radical that is. In Young's experiment, a slit was a gap cut into a solid barrier, an opening that light passes through. But you cannot cut a hole the size of one atom into a wall and expect anything sensible. So the MIT team inverted the whole idea. Instead of a hole that light passes through, they used an atom that light bounces off of. When a photon comes in and interacts with a single atom, the atom can scatter it, redirecting the photon into a new direction. And scattering off two nearby atoms is, for the purposes of interference, exactly like passing through two nearby slits. The photon has two possible scattering locations, the left atom or the right atom, and those two possibilities are the two paths. As Fedoseev put it, these single atoms are like the smallest slits you could possibly build. There is no barrier, no material, no machined opening. There are just two atoms floating in the geometry of light, and a photon that might scatter off either one. To make the experiment truly clean, one more thing was essential. The light had to be faint, desperately, deliberately faint. So faint that, on average, only a single photon scattered off a single atom at a time. This is the atomic version of dimming the source until photons trickle out one by one, the very thing that made the original single photon double-slit result so haunting. If a flood of photons had poured in, the picture would be muddied by crowds. By keeping it to one photon and one scattering event at a time, the team ensured that whatever happened to a single photon interacting with the purest possible slit, an individual atom entirely alone. Then they scattered their photons, gathered the light that came off, and looked to see what pattern it made. But we should be careful about the word pattern here, because it hides something important about how an experiment like this actually works. A single photon scattering off a single atom does not, by itself, paint a row of stripes. It produces exactly one outcome, one photon caught at one place. The interference pattern is not a thing any individual event displays. It is a portrait that emerges only from a great many events laid on top of one another. The same way Young's fringes only appeared after thousands of lonely dots piled up. So the team did not rely on a single pair of atoms and a single photon. They prepared their lattice with more than 10,000 atoms at once, a vast, orderly army of identical single atom scatterers, and they ran the scattering over and over, gathering photon after photon under conditions prepared to be as nearly identical as physics allows. Each atom, each event, contributed its one small piece of evidence, and only when all those pieces were stacked together did the shape of the whole reveal itself, either the crisp banding of preserved interference or the flat blur of interference destroyed. This matters for honesty's sake. Nobody watched a lone photon decide to be a wave. What the physicists measured was a statistic, a tendency written across an enormous ensemble of single events. Each one individually humble, the pattern living not in any one of them but in their sum. The relevant physics, the scattering, always came down to one photon and one atom. The visible result always came from the multitude. And this is where the machinery of the last 100 years finally paid off. Because the MIT team could do something Einstein and Bohr never could. They could tune the slit. To understand what they tuned, we need to talk about two ways that light can scatter off an atom, because the entire result hinges on the difference between them. Physicists call them coherent scattering and incoherent scattering, and while the names sound technical, the idea underneath is something you can picture. Coherent scattering is clean. When a photon scatters coherently off an atom, it leaves no trace behind. The atom is not changed. It does not recoil in any recorded way. It does not get nudged into a new state. It keeps no memory that the photon was ever there. The photon bounces off and flies on, and afterward there is no evidence, anywhere, of which atom did the scattering. Because coherent scattering leaves no record, the two possible paths, the left atom and the right atom, remain genuinely indistinguishable, and indistinguishable paths, as we learned, are exactly the condition for the wave to live. Coherent scattering preserves the interference pattern. It is the wave-friendly kind of bounce. Incoherent scattering is messy. When a photon scatters incoherently, it leaves a mark. It kicks the atom, changes its state, jostles it in some way the atom retains, so that afterward, the atom itself carries a record of the interaction. And if the atom that scattered the photon has been changed by the encounter, then in principle you could examine that atom, read the change, and figure out that this atom, not its neighbor, was the one that did the scattering. Which means the path is no longer indistinguishable. Which path information now exists, imprinted in the atom, and which path information, as Bohr insisted a century ago, kills the wave. Incoherent scattering destroys the interference pattern. It is the particle-friendly kind of bounce. And here is the elegant part of how the team actually read all this, because they never needed to interrogate the atoms one by one. The two kinds of scattering announce themselves directly in the light that comes off. Coherent scattering, the trace-free kind, is what assembles into the sharp interference fringes on the detector. Incoherent scattering, the kind that leaves a record in a recoiling atom, cannot contribute to those fringes. So it shows up instead as a diffuse, structureless background, a soft haze of light spread behind the crisp bands. The two are visibly different. Sharp stripes are the wave speaking, coherent light that kept the paths indistinguishable. A washed out glow is the particle speaking, incoherent light that left the roux on record. So the physicists could gauge how much which path information the world had captured simply by measuring the balance between the two in the scattered light. How much went into crisp fringe, and how much bled into background haze. No one had to pick up a single atom and inspect it. The light itself carried the tally, the ratio of sharp to blurred reporting, exactly how much of the photon's secret the atoms had quietly written down. So the fate of the whole experiment comes down to a single question. When a photon scatters off one of these atoms, does it scatter coherently, leaving no trace and preserving the wave? Or does it scatter incoherently, leaving a record in the atom and killing the wave? And the genius of the MIT setup is that they could dial the answer. They could tune, smoothly and controllably, how much of a record the atom kept. They could turn a knob and slide the experiment from wave to particle, and everywhere in between. The knob was the atom's fuzziness. Recall the uncertainty principle from earlier, the deep law that says a quantum object cannot have both a perfectly sharp position and a perfectly sharp momentum. That principle is not an abstraction here. It is the star of the show. Each atom in the lattice is a quantum object, and it does not sit at a mathematically precise point. It occupies a small, blurry cloud of possible positions, a region of quantum uncertainty, Physicists sometimes call this spread the atom's spatial wave packet, but the plain language word the MIT team themselves used over and over was fuzziness. Each atom is a little fuzzy ball of position uncertainty, and the size of that fuzzy ball is something you can control by adjusting how tightly the laser lattice grips the atom. Squeeze the lattice hard, clamp down on the atom, and you force it into a very small, very sharply defined position. Its fuzzy ball shrinks. But by the uncertainty principle, pinning its position tightly means its momentum becomes wildly uncertain, spread across a huge range. Loosen the lattice, let the atom relax, and its position blurs out into a larger, fuzzier cloud, while its momentum becomes more sharply defined. Tight position, blurry momentum. Blurry position, tighter momentum. The trade is unavoidable, and the MIT team could set it wherever they liked, simply by adjusting their lasers. Now watch how that connects to the photon's path, because this is the heart of the entire result. When a photon scatters off an atom, it delivers a recoil kick. Exactly the momentum kick Einstein invoked with his spring a century ago. Conservation of momentum demands it. The photon changes direction, so the atom must recoil to balance the books. The question is whether that recoil leaves a readable record, and the answer depends on the atom's fuzziness, on how sharply its position and momentum are defined. Consider an atom pinned very tightly, with a sharp position and therefore, by uncertainty, a very blurry momentum. When the photon kicks it, the atom does receive a recoil, but the atom's momentum was already smeared across an enormous range of values. So the tiny added kick from the photon is lost in the noise. It is like trying to notice one extra gust of wind in the middle of a hurricane. The atom's momentum was so uncertain to begin with that the photon's recoil leaves no distinguishable mark. There is no readable record of which atom scattered the photon. The path stays indistinguishable. The scattering is coherent. The wave survives, and the interference fringes appear on the detector. Now consider the opposite. An atom relaxed and loose, with a fuzzy, spread out position, and therefore a more sharply defined momentum. When the photon kicks this atom, the recoil now stands out. Because the atom's momentum was well defined to begin with, the added kick from the photon is a noticeable, measurable change, a signal that rises above the background. In principle, you could look at the atom afterward, see that its momentum had shifted by exactly the recoil, and conclude that this atom did the scattering. A record has been written. Which path information now exists, imprinted in the atom's recoil? The scattering is incoherent. The wave dies and the fringes wash away into a featureless blur. And crucially, everything in between is available too. The team could set the fuzziness to any intermediate value, and there they saw exactly what quantum mechanics predicts: a partial result. Partial which path information, and partial loss of the wave. The fringes did not blink out all at once. They faded, smoothly and gradually, growing dimmer as the atoms carried more and more of a record about the photon's route. Turn the knob toward more path information, and the wave visibility drops. Turn it back toward less, and the fringes brighten again. This is the single most important measurement in the entire experiment, so let it land clearly. The more distinguishable the photon's two paths became through information stored in the atoms, the less visible the interference pattern grew, not by magic, not by an all-or-nothing switch, by a smooth, quantitative trade, exactly the trade Bohr described. now measured with the precision Bohr never had. This is complementarity, caught in the act and dialed like a volume knob. Wave on one end, particle on the other, and a continuous slope between them, every point of which matched the prediction of quantum theory. Einstein's dream of having both at once was not merely denied at the extremes, it was ruled out across the entire range, measured point by point, with individual atoms as the slits. But the team was not finished, because there was still that century-old loophole, that stubborn maybe, hanging in the air. A skeptic could still say, as skeptics had said since 1927, that all of this was really about the spring, that the fringes died not because of information, but because the atom got physically kicked around, mechanically disturbed, jostled by the recoil the way Einstein's sprung barrier would have been jostled. In this telling, the trap is holding the atom like a spring, and it is the spring, the physical confinement and its disturbance, that smears the pattern. Information might have nothing to do with it. It might just be mechanics, clumsiness in fancy dress. So the MIT team did the thing that finally separated the two stories, and the thing that no experiment for 100 years had cleanly done. They removed the spring. They took the atoms and released them from the lattice entirely. For a brief, precious window, the atoms floated completely free in the vacuum, held by nothing, gripped by no laser, suspended in empty space before gravity would pull them down. No trap, no confinement, no spring of any kind. If the fringe destruction was really about the mechanical disturbance of a confined, spring-held atom, then removing the spring should have changed the result. The loophole should have opened. The skeptics maybe should have finally paid off. It did not. With the trap gone and the atoms floating free, the results were the same. The coherence properties of the scattered light did not depend on whether the atoms were held in the lattice or drifting untethered in the vacuum. Whatever was killing the wave, it was not the spring. Fedoseev stated it as plainly as it can be stated. In many descriptions, he said, the springs play a major role, but the MIT experiment showed that no, the springs do not matter. What matters is only the fuzziness of the atoms. Read that again, because it is the hammer blow that ends a 100-year argument. The springs do not matter. Einstein and Bohr fought over springs and recoiling barriers because that was the physical picture they had, and the whole debate seemed to hinge on the mechanics of a disturbed slit. But the MIT team showed that you can throw the spring away entirely, and the trade between path and wave persists, untouched. The mechanical disturbance was never the deep cause. It was a distraction, a piece of scaffolding everyone mistook for the building. Strip it away, and the real thing stands exposed. What determines whether the wave lives or dies is not whether the atom gets physically shoved. It is whether the atom ends up carrying distinguishable information about the photon's path. And what carries that information, once the spring is gone, is something subtler and more fundamental than any mechanical kick. It is the quantum correlation between the photon and the atom, a link the physicists describe as atom-photon entanglement. When the photon scatters in a way that leaves a readable trace, the photon and the atom become correlated, their fates woven together, so that the state of one is bound up with the state of the other. The witch path information does not sit in the photon alone or the atom alone. It lives in the correlation between them. In the shared quantum system they now form together. And it is the existence of that correlation, the fact that the two paths have become distinguishable in the joint state of atom and photon. That determines whether interference can appear. That word, entanglement, deserves a plain unpacking, because it is the true engine here, and it gets mythologized more than almost anything in physics. Strip away the mystique, and entanglement just means this. Two objects can end up in a joint state where neither one has a fully definite identity of its own, and yet their properties are locked together, so that pinning down one would tell you something about the other. When a photon scatters off an atom and leaves a readable trace, the photon and the atom fall into exactly this kind of shared state. The photon's root and the atom's recoil become two ends of a single correlated fact. You cannot fully describe the photon by itself anymore, because part of its story now lives in the atom. And that is precisely why the two possibilities can stop interfering. The instant the photon's path becomes tied to a distinguishable state of the atom, went left and went right are no longer the same clean situation folding back together into a wave. They have become two different combined situations, photon plus left atom and photon plus right atom, and situations that differ in the atom cannot recombine as if the atom were not there. The braid, once tied, cannot be undone by pretending the atom is not part of the story. This is the real mechanism the MIT experiment isolated, laid bare with no spring and no apparatus to muddy it, and it points straight at the last, most misunderstood question of all. This is why the springs were always beside the point. A spring is a mechanical thing, a matter of forces and confinement and physical jostling. But the death of the wave was never fundamentally mechanical. It was informational. It was about whether the universe, in the correlated quantum state of the photon and the atom together, ended up holding a reliable answer to the question of which path was taken. When the fuzziness was set so that no such answer could be read, the paths stayed indistinguishable. The correlation carried no usable which path information, and the wave lived. When the fuzziness was set so that the recoil became readable, the correlation carried the answer. The paths became distinguishable, and the wave died. The spring was never the judge. The information was. As Ketterle summarized the deeper lesson, you cannot describe what happens here with simple mechanical pictures of springs and pushes. One has to use a more profound description, he said, one that uses quantum correlations between photons and atoms. The photon and the atom are not two separate things touching and shoving. They are becoming one linked system, and the information distributed across that system is what dictates which face of the photon, wave, or particle can show itself. Notice what the MIT team accomplished by building the slits from single atoms and then removing the trap. They did not discover a new law. They did not overturn quantum mechanics or catch it breaking its own rules. Quantum theory predicted every single thing they measured. The coherent scattering, the incoherent scattering, the smooth fade of the fringes, the irrelevance of the spring, all of it with textbook precision. What they did instead was something arguably more unsettling. They removed every excuse. For 100 years, a skeptic could always mutter that complementarity was merely a practical limit of imperfect hardware, that a gentle enough detector or a delicate enough spring might someday let you cheat the trade. The MIT experiment took that hope and dismantled it piece by piece. It stripped the double-slit experiment down to its irreducible core. 2 single atoms and 1 photon, with no barrier, no material, and finally no spring at all. And the trade was still there, untouchable. Built not into the apparatus, but into the way quantum information distributes itself between light and matter. There is a lovely subtlety buried in the team's own paper, and it sharpens the whole result. So it is worth slowing down for. Why is the version built from two independent atoms the clean one? Because of where the record of the path ends up living. When the two atoms are genuinely separate, each free to move on its own, the photon scatters off one of them and only that one recoils. The kick lands on a single atom, and which atom carries the kick is, all by itself, the record of the route. Left atom recoils, the photon went left. Right atom recoils, the photon went right. The which path information sits in a plain physical fact. The location of the recoil, present in the world whether or not anyone ever checks it, and about as unambiguous as a record can be. Now contrast that with the case Einstein and Bohr actually spent their most famous exchange arguing over a single movable slit, or two slits rigidly locked onto one shared mount. There, the path is not marked by which of two independent things moved. It is buried instead in a delicate phase, a subtle timing relationship inside the shared object's quantum state, and that phase can quietly wash out if the scattering unfolds slowly, compared to the natural rhythm of the trap holding everything in place. In that configuration, the record can erase itself, and the question of when interference survives becomes genuinely tangled and case-dependent. So the two giants, it turns out, had planted their flag on the more complicated and subtle ground, the coupled case, while the cleanest, most transparent version of their own question, two independent, separately movable slits, went unbuilt and unexamined for 100 years. When you finally assemble it out of two independent atoms, the fog lifts. The record is simply where the recoil landed. Their instinct, Bohr's especially, turned out to be right, but for reasons deeper and cleaner than either of them could have measured at that chalkboard in Brussels. And so we arrive at the sharpest possible statement of what the experiment found. The two slits were single atoms. The record of the path lived in the recoil, in the fuzziness, in the quantum correlation between the atom and the photon. When that correlation held a readable answer to which atom scattered the photon, the interference faded in exact proportion to how readable it was. When it held no such answer, the fringes returned in full. No spring required to explain it. No mechanical disturbance needed. No clumsy detector to blame. Just information distributed across a correlated quantum system of light and matter, deciding which face of the photon the universe would allow you to see. And the team is not stopping there. Even the cleanest experiment opens a door to a stranger one. And the MIT group has already named their next move. So far, every slit has been a single lone atom in its own pocket of the lattice. But they now want to load two atoms into each site instead of one, and let them interact, and watch what a photon does when it scatters from a pair of atoms that are themselves quantum correlated with each other before the light ever arrives. As Hans and Lin put it, the interactions between the atoms at each site may give interesting results. Nobody yet knows exactly what those results will be, which is precisely why the experiment is worth doing. Each time physicists strip this old puzzle down and rebuild it from smaller, purer parts, it hands back something they did not expect to feel. The double-slit experiment, 100 years on, is still not finished teaching, which leaves one enormous question still standing, the one that has haunted the phrase "which path information" since the moment we introduced it. Throughout all of this, The interference vanished whenever a record of the path existed. But existed for whom? Nobody in that laboratory was staring at individual atoms, reading their recoils, consciously noting left or right. The photons scattered, the fringes faded or survived, and the pattern built up on the detector whether or not any human being ever inspected which atom did what. So if no person needed to look, if no conscious mind had to read the record for the wave to die, then what does it actually mean to say the universe knows the path? What is doing the knowing? That question is where the deepest misunderstanding of this entire experiment lives. The one that has launched 1,000 mystical headlines. And it is where we turn next. There is a sentence that has attached itself to the double-slit experiment like a barnacle, and it has done more damage to public understanding than almost any other claim in physics. The sentence is some version of this. The particle behaves differently when it is being watched, as if it knows it is being observed. From that seed grow 1,000 headlines and late-night videos insisting that human consciousness creates reality, that the universe rearranges itself when a mind looks at it, that we are all somehow dreaming the cosmos into being. It is seductive, it feels profound, and the MIT experiment, more cleanly than anything before it, shows exactly why it is wrong. Let us settle this carefully, because the whole meaning of what those atoms revealed depends on getting it right. Go back to what actually made the interference disappear. It was not a gaze, it was not attention, it was not a scientist leaning in to check. It was a physical record, written into the recoil of an atom, encoded in the quantum correlation between that atom and the photon. The wave faded in exact proportion to how readable that record was, and it faded whether or not a single human being ever read it. The atoms did their scattering, the correlations formed, the fringes dimmed or brightened, and the pattern accumulated on the detector regardless of who was in the room or whether anyone was looking at all. Nobody sat there reading recoils off individual atoms and consciously deciding left or right. There was no such person. There did not need to be. This is the point that dissolves the mysticism. When physicists say a photon was observed, they do not mean a mind perceived it. They mean the physical world recorded distinguishable evidence of what it did. Observation in quantum mechanics is not an act of awareness. It is an act of interaction. It is the universe entangling one thing with another, so that information about the first becomes physically present in the second. A photon scattering off an atom and imprinting its path into that atom's recoil is a measurement. In the full quantum sense, even if the atom is floating alone in a sealed vacuum chamber with no observer anywhere nearby, the measurement happened when the correlation formed. The consciousness of an experimenter is not a variable in any of the equations. It never was. Think about what this means for the famous claim that particles know they are being watched. Nothing in the MIT experiment, or in any version of the double-slit experiment, requires a photon to know anything. The photon does not sense a detector and change its behavior out of shyness. What happens is far more mechanical and far less magical. Either the photon's two possible paths leave distinguishable physical records in the world, or they do not. If they do, the alternatives cannot recombine into an interference pattern, because they have become genuinely different physical situations, correlated with different states of the atoms. If they do not, the alternatives remain indistinguishable and add together into a wave. The photon is not deciding. It is not aware. It is simply subject to a rule about when possibilities can combine and when they cannot, and that rule is triggered by physical information, not by minds. An analogy helps, as long as we hold it loosely. Imagine two roads leading to the same town, and imagine that whether they merge smoothly at the end depends on whether anyone kept a logbook of which road each traveller used. If no logbook exists anywhere, the travellers arrive with their routes forgotten, indistinguishable, and their arrivals blend together. If a logbook does exist, tucked in a drawer that no one ever opens, the routes are on record, distinguishable, and the blending fails. The blending does not care whether anyone reads the logbook. It cares only whether the logbook exists. The atom's recoil is that logbook. It can sit unread in the drawer of the universe forever, and its mere existence is enough, no reader required. This is why environmental information alone destroys interference, why the mere presence of a physical record, entirely unobserved by any mind, is sufficient to erase the wave. And once you see it this way, the phrase "witch path information" stops sounding spooky and starts sounding almost boring, in the best possible sense. Information here is not a mental thing, it is a physical thing. It is a correlation. It is one object's state depending reliably on another object's history. The universe is full of such correlations constantly forming, everywhere, all the time, with no observers involved. Every interaction between particles leaves traces. This ceaseless, observerless imprinting of information into the environment has a name, and it is the real engine behind why we do not see quantum weirdness in everyday life. Physicists call it decoherence. We should mention decoherence briefly and carefully because it is the natural extension of everything the MIT atoms showed, though it must stay secondary to the experiment itself. Decoherence is what happens when a delicate quantum superposition, two indistinguishable possibilities woven together, leaks information into its surroundings. A large object, a speck of dust, a cat, a chair, is constantly colliding with air molecules, absorbing and emitting photons, entangling itself with a vast environment. Every one of those interactions is like a photon and scattering off an atom, imprinting witch path information into the world. For anything bigger than a few atoms, this happens so overwhelmingly fast and so thoroughly that the record of any given path is written into the environment essentially instantly and irreversibly. The alternatives become distinguishable at once, and the wave-like blending vanishes before it could ever be seen. This is why you never catch a coffee mug behaving like a wave. Not because it is too big in some vague sense, but because it is too entangled with everything around it. The information about where it is has already flooded into the universe. Decoherence is the double-slit trade playing out ceaselessly, on everything, all the time, with no one watching. The MIT experiment is, in a way, decoherence caught in its purest and most controllable form, dialed up and down by hand, an atom at a time. Now we can be honest about what the experiment did and did not prove, because a fair account demands the distinction, and the temptation to overclaim is exactly what leads to bad science. What it demonstrated, as a confirmed experimental result, is complementarity, cleaner than ever before. It showed the smooth, quantitative trade between witch path information and interference visibility. It showed that the trade survives even when the slits are single atoms, even when the trap is removed, even when there is no spring and no mechanical disturbance to blame. It showed that the essential factor is the quantum correlation between photon and atom. the distribution of information across a joined system. These are measurements. They matched quantum theory's predictions with precision. They closed Einstein's specific loophole, the hope of reading the path from a recoil while keeping the wave, because the experiment probed exactly that idea and found it does not hold. All of that is solid ground, but we must be equally clear about what the experiment did not do. It did not prove which interpretation of quantum mechanics is correct. And this is a real and important distinction, because complementarity, the observed rule, is not the same as any single philosophical story about why the rule holds. There are several such stories, and physicists genuinely disagree about them, not because the math is unclear, but because the math is silent on the question. The equations of quantum mechanics tell you what you will observe with breathtaking accuracy. They do not tell you what is really happening between the moment a photon is prepared and the moment it is detected. Into that silence, different interpretations speak. The Copenhagen interpretation, associated with Bohr himself, says roughly that it is meaningless to ask which path the photon took when no measurement distinguished it. That the photon simply has no definite path in that situation, and that quantum mechanics describes our knowledge and our measurements, rather than a hidden underlying reality. On this view, complementarity is fundamental, and there is nothing deeper to find. The many worlds interpretation says something wilder, that all possibilities are equally real and the universe branches, so that the photon really does go both ways, in different branches that decohere from one another, and interference is what you see when the branches have not yet been distinguished. The pilot wave interpretation, sometimes called Bohmian mechanics, says the photon always has a perfectly definite path, guided by a real physical wave, and that the wave is what interferes while the particle rides along it, with the appearance of randomness coming from our ignorance of the exact starting conditions. These are radically different pictures of reality, and here is the crucial fact. All three predict exactly the same result for the MIT experiment. All three reproduce the smooth trade between path information and interference. The experiment cannot tell them apart, because they were built to agree on every observable outcome, and to differ only in the story underneath. So when a headline announces that the double-slit experiment proves the Copenhagen interpretation, or proves many worlds, or proves that the photon takes both paths as real objects, it is overreaching. The experiment supports complementarity. It does not crown a philosophy. It is entirely consistent with a photon that had a definite path all along, as pilot wave theory insists, and equally consistent with a photon that had no path at all until measured, as Copenhagen insists. The observed rule is agnostic about the metaphysics. Anyone who tells you the experiment settles what a photon really is between preparation and detection is selling you their favorite interpretation dressed up as a discovery. There are other famous variations worth knowing exist, though they too must stay in the background, because they can be misread as overturning what the atoms showed, when, in fact, they deepen it. The quantum eraser is one. In an eraser experiment, physicists first record which path information, killing the interference, and then cleverly erase that information before it can ever be read, scrambling it so thoroughly that the path becomes unknowable again. When they do, the interference can be recovered, not for the individual detections in isolation, but in the correlations, once the erasure is accounted for. This sounds like magic, like undoing a measurement, and it is often reported that way. But it is not magic, and it is not consciousness. It is a further confirmation of the same principle. Interference is present exactly when the path is physically indistinguishable, and absent exactly when it is distinguishable. And if you genuinely destroy the record before it becomes irreversible, you restore indistinguishability and the wave-like correlations return. The eraser does not let a mind reach back and change the past. It shows, once more, that information availability, not observation by a person, is what governs the wave. The delayed choice experiments are another such variation, in which the decision of whether to record the path is made after the photon has already passed the slits. These experiments feel as though they let you change what the photon did in the past by choosing later, which has fueled endless confusion about retrocausality and consciousness reaching backward in time. But once again, the honest reading is more modest and more consistent. What the delayed choice results actually show is that it was never legitimate to assign the photon a definite wave story or particle story while it was in flight in the first place. The photon's behavior is not a property it carried, and that your later choice retroactively edits. It is a fact about the entire experimental arrangement, including which information ends up available, and that arrangement is only complete once the whole thing has run. No signal travels backward. No past is rewritten. The lesson is the same lesson the atoms taught, that wave and particle are not costumes the photon wears in transit, but descriptions tied to what the whole setup, information and all, permits you to see. Every one of these variations, then, orbits the same center of gravity, the same rule the MIT experiment exposed in its most naked form. And it is worth saying plainly what that rule is not, because the misconceptions are so persistent. Wave-particle duality does not mean the photon is a tiny classical ball that suddenly transforms into a literal water wave and back again. There is no morphing, no shape-shifting object flickering between two physical forms. The photon is one kind of thing, a quantum entity, and wave-like and particle-like are two complementary descriptions of how that single kind of thing can manifest, depending on what the experiment makes available. It does not travel through both slits as two ordinary objects, and it does not decide which face to show based on being watched. The atoms did not decide which path the photon took. The photon did not know it was being observed, and no conscious act collapsed anything. These phrasings are not just imprecise, they point the mind in exactly the wrong direction, toward a universe that responds to attention, when the truth is a universe that responds to information. So what, in the end, made this old experiment even stranger? Not a new law. That is the first thing to hold on to as we draw the threads together. The MIT team did not break quantum mechanics, did not violate its rules, did not discover a loophole or a paradox or a crack in the theory. Every result they obtained was predicted by quantum mechanics with full confidence beforehand. In the narrowest sense, they found exactly what a century of theory said they would find. If strangeness meant surprise, there was no surprise. The strangeness is of a deeper kind, and it is the kind worth ending on. For 100 years, the double-slit trade could always be partly explained away as a consequence of ordinary machinery. The slits were cut into real material. The detectors were built from atoms and wires. The barriers had mass and springs and could be jostled and disturbed. And so a stubborn intuition could always survive, whispering that maybe the wave died because the equipment was clumsy, because measuring meant shoving, because a gentle enough touch might someday let you have the path and the pattern both. The mystery could be blamed on the crudeness of the tools, What the MIT experiment did was take away the tools, one by one, and showed that the mystery remained. It replaced the barrier with single atoms, the smallest slits that can exist. It ensured only one photon scattered at a time. And then, in the move that mattered most, it removed the trap entirely, let the atoms float free, took away the spring that Einstein and Bohr had argued over for years, and the trade held anyway. The fuzziness of the atoms, the quantum correlation between light and matter, the sheer availability of information about the path, that was all it took. Strip away every mechanical excuse, remove everything a skeptic could point at and blame, and the rule does not weaken or dissolve. It stands there exposed, in an almost irreducible form, with nothing left to hide behind. That is what got stranger. Not the behavior of the universe, which was the same as always, but our inability to explain it away. The experiment made the paradox harder to dismiss, harder to attribute to sloppy detectors, or heavy barriers, or trembling springs. It showed the boundary between knowing and seeing is not a smudge left by imperfect instruments. It is woven into how quantum information distributes itself between a photon and the matter it touches. And so, nearly a century after two of the greatest minds who ever lived stood at a chalkboard in Brussels and fought over a slit on a spring, physicists can now build the equivalent of that slit out of a single atom, cool it to the edge of absolute zero, hold it in a web of light, and release it into empty space. They can do the thing Einstein and Bohr could only imagine, the pure thought experiment made real. And when they do, the universe still enforces the same unsettling rule the two of them argued about. When reliable evidence of the photon's path is preserved anywhere in the physical world, the interference fades. When the paths remain genuinely indistinguishable, when no record of the route survives, the wave-like pattern returns. You may have the path, or you may have the wave. The world does not permit you to fully reveal both in the same breath. Sit with the shape of that boundary, because it is the real inheritance of this experiment. It is not a limit on our instruments. It is not a fact about human perception. It is a statement about how much of reality can be laid bare at once. The photon and the atoms are not separate things standing at a distance. They become a single correlated quantum system, their states woven together, and the information spread across that joint system decides which aspect of the photon is allowed to appear. Ask the system where the photon went, and it will answer, but in answering, it spends the wave. Ask it to show you the wave, and it will, but only by keeping the path forever unspoken. The two questions are not both answerable at the same time, not because we are too clumsy to ask them, but because the universe does not hold both answers in a form that can be simultaneously revealed. Notice what this does not say, because the ending matters and the temptation to overreach is strong. It does not say reality is imaginary, or that nothing exists until observed, or that consciousness conjures the world, or that we live in a simulation, or that some other dimension is leaking through. The MIT atoms say none of that, and they gently refute the mystics who would claim they do. There is no evidence here that a mind is needed, and every indication that the world records its information whether or not anyone is watching. The photon is real. The atoms are real. The correlation between them is real and physical and unmysterious in its mechanism. What is strange is not that reality is a dream, but that reality is complete, consistent, and precisely predictable, and yet still refuses to let us hold all of its classical properties in our hands at the same moment. The refusal is not a gap in our knowledge waiting to be filled. As far as this experiment can show, the refusal is the way things are. And there, honesty, is where the mystery is left, not resolved, but relocated. Quantum mechanics predict the trade between path and pattern with an accuracy that is almost embarrassing in its perfection. There is no question about what will happen when you run the experiment. The equations never miss. But underneath that flawless prediction lies the question the equations do not answer, and this experiment does not settle. The question Einstein really cared about and Bohr really wrestled with. The question of what a photon actually is in the silent interval between the moment it is prepared and the moment it is caught. Is it a particle that always had a definite path we simply cannot know? Is it a wave of pure possibility that only becomes definite when measured? Is it something that branches into every outcome at once? The experiment is consistent with all of these and decides among none of them. It tells us, with total confidence, what the universe will do. It leaves gloriously open the question of what the universe is. That is the note to end on. Not a solved riddle, but a sharper one. 100 years of progress took us from two men arguing over a spring to a laboratory building slits out of single atoms. And at the end of that century of extraordinary effort, the deepest strangers did not disappear. It was clarified. It was stripped of its excuses and its clutter until only the essential thing remained, the clean, irreducible boundary between knowing the path and seeing the wave. We can now demonstrate that boundary more purely than Einstein or Bohr ever could. We understand exactly what triggers it: information, correlation, the physical availability of the answer, and we know it needs no observer, no consciousness, no magic, and still, standing at the edge of it, holding the cleanest version of the experiment ever performed, we are left facing the same quiet, unanswerable question they faced, dressed now in single atoms and laser light. The universe will always tell us what it does. It has never once agreed to tell us completely what it is.